You most likely learned about extreme values last year in pre-calculus. So extreme values, or extrema, by the way, extrema is plural of extremum. Extreme values are the maximum and minimum values of a function. We have several types of maximum and minimum values. The first type is the local maxima and minima. By the way, maxima is the plural of maximum, and minima is the plural of minimum, just so you know. So the local maximum or local minimum will occur when you have a peak or a valley. So I'll show you a picture in just a second. The absolute minimum and maximum are going to be at the highest and lowest points over an entire interval. So I'm going to draw you a picture, and then I'll label all of our extreme values. So I've drawn a function here, and I would like to point out a few of the important features of the function. So the first thing is that at these 2 points right here, I have a local maximum value. And at this point and this point, I have a local minimum value. I want you to notice that this one on the right is actually not differentiable. It has a corner in it. That's fine. That actually happens. You can still have a local minimum value there. That's totally okay. The other thing I would like to point out is that this point right here is not only one of my local maxima, it's actually my absolute maximum. It's the highest point on the entire graph. The other thing that I have is I have this endpoint here, and you'll notice that's the lowest point on my graph. That is my absolute minimum. I do want to point out that this endpoint is, just because I have an absolute max there or absolute minimum there, it doesn't necessarily mean it's local. A local max or a local min are only going to occur at peaks on the graph, and that's where the local maxes are going to occur, and a local min will only occur at a valley. So you need to have if you look at those 2 minimum values, for example, you'll notice that the graph goes down, it touches the minimum, and then it goes back up. For the local max values, it goes up, touches the max value, and then goes down. So if you have an endpoint, that's actually not going to be a local minimum, even if it is the absolute minimum. This other endpoint there's actually really nothing there. The other thing that has nothing going on is this point right here. It looks like that might be something, that is going to be something that we're going to talk about later on. We call it a point of inflection, but it's not actually a max or a min. So we're not going to worry about that right now. You'll notice that the graph goes up, it hits that point, but then it keeps going up. So it's not going to be a max or a min. So just a little theorem. This is actually called Fermat's theorem. If you are interested in math history, Fermat actually has other theorems. There's one called his last theorem that took over several hundred years to prove. It is an interesting story if you want to read about it. So basically what this says is that if your graph has a local max or a min, and also if your derivative exists, then your derivative equals 0. So on the previous page, you might have noticed there was one thing that had a cusp. In that one, the derivative didn't exist, but all of the other local maxima and local minima had a derivative of 0. In order to find our local maximum, we're actually going to use the idea behind Fermat's theorem, and we are going to find what's called critical numbers. And a critical number is an x value where your derivative equals 0 or where your derivative does not exist. I do want to warn you that just because you get a derivative of 0, it doesn't necessarily mean you have a max or min, but it means that you might have a max or min. So that's how you find your max and min values. By the way, critical numbers are also referred to as critical values or critical points. So critical numbers are the x values. The maximum and minimum values are actually going to be the y value. So let's actually do an example where we find our absolute maximum and our absolute minimum. For first example, we have the function f of x equals 3x to the fourth minus 4x cubed over the interval -1 to 2. So we're going to find our absolute extrema. The first thing that we're going to do is find our critical values. So let's do that first. And remember, critical values we can find by taking the derivative and setting it equal to 0. You also are going to find where it's not differentiable. This one, though, is actually differentiable everywhere because it's a polynomial. So we take our derivative, we get f prime of x is equal to 12x cubed minus 12x squared. I'm going to set that to 0, and I can factor out a 12x squared. That leaves me with x equals 0 and x equals 1. The first thing I want you to make sure of, by the way, for your critical values is make sure that they're actually in that interval. If they're not in that interval, then you don't need to use them at all. The other thing that we need to do is we need to use our endpoints. So what I'm going to do is I'm going to look at my f of x value. I'm going to plug in, first of all, I'm going to plug in my endpoints, and then I'm also going to plug in my critical values. I don't know if you remember, I mentioned earlier that absolute extrema occur when the derivative is 0, or they also will occur at the endpoints. So just keep that in mind. So I have two critical values, which is when the derivative is 0. These are my critical values. And I also have two endpoints. By the way, you'll notice I kept saying critical values. Critical numbers, critical values, just remember those are the same thing. Critical points, another name for them. All three of those are acceptable ways to call these values. So then these two on the outside, of course, are my endpoints. We need to check all of those. So what we're going to do is we are going to substitute in each of these x values to my original function. Please do not substitute it into the derivative. If you do, you'll get 0 for the middle two, and the first two aren't really going to be meaningful. So we are going to substitute in -1 to my original equation. When I do that, I get 7. You can do the same with all of the other ones, and you'll find that you end up getting these values right here. So now what I can do is I can look at these f of x values, my y values, and I can see which one is the largest and which one is the smallest. The largest number is going to be an absolute maximum, and the smallest number is an absolute minimum. So you'll notice my largest value is my absolute max. It's 16. My smallest value, my absolute minimum, is going to be -1. Remember what I just said, that my maxima and minima are y values. So I'm going to show you how we're actually going to write out our statement here. So I gave you kind of a template that you can use every time you get one of these types of problems. Please make sure that you mention the y value. So the absolute maximum was 16, and that occurred at x equals 2. The absolute minimum value was -1, and that occurred at x equals 1. So just make sure that you mention the y value. The x value is less important, but it's not a bad idea to mention that. But your final answer for this is actually the y value.